Now we have Vikraman Chowdhury discussing how to embed purity in an impure language via the use of a comonad.
Hello, I'm Vikraman Chowdhury, and I'm going to be presenting some joint work with Neil Krishnaswamy on our paper, Recovering Purity with Comonads and Capabilities. The basic problem in this paper is the following. We've known for a while now how to extend a purely functional language with monads to encode side effects. However, what if we already have an impure functional language? Can we extend the type system to encode the absence of effects? So let's try to motivate why such a thing might be useful with some examples. Consider a strict call-by-value language which allows side effects, and let's consider the map functional. So map is a higher order function which takes a function f and applies it to every element of the list recursively. There are at least two different ways of writing map. In map1, we recursively call map1 on the tail of the list before evaluating f on the head of the list. In map2, we evaluate f on the head of the list before recursively calling map2 on the tail of the list. So these two functions should be equal, but in an impure language like this, they can have different side effects. So as an example, let's evaluate map1 and map2 on the following inputs. So here f is the identity function on strings, but it's impure. It prints its input string to standard out before returning it. So let's try to reduce map1. We expand the let, and we observe that it reaches the end of the list when it tries to evaluate f on the string right. So this prints right. Reducing more, we see that it calls f on 2, which prints 2. And then it calls f on left, which prints left. And finally, it returns the original list. So it produced a side effect where it printed right to left. If, however, we reduce map2 on the same inputs, we notice that it evaluates f first on the string left, then on the string 2, and then on right, and finally returns the original list. So even though both of these map functions return the same output, they produce different side effects. Alternatively, consider these two functions f and g from int to int. They perform different side effects before returning their output. Now, suppose we map g on xs, followed by mapping f on the output. An optimizing compiler could perform map fusion on this expression. But in this impure language, if we mapped f compose g on xs, that would produce a different side effect. So this map fusion optimization pass would be invalid. So I hope these examples are motivating, and they show that it would indeed be useful to be able to encode the absence of effects in an impure language. So first, let's see how effects are being encoded in this language with some examples. Let's consider this function g. It takes a channel C, a string S, prints S on the channel C, then returns S. So this function is impure because it uses the channel it was passed to perform an effect. Now consider this function f from string to string. This is also impure, but it is defined by partially applying g to standard out. Now, standard out is a channel that's available in the global environment. So there is a difference between f and g. G is safe because it uses the channel that was passed as an argument, but F uses standard out, which is used from the global environment. So this gives us an idea. We should be able to control the use of effects by controlling the channel variables that a function has access to in its environment. So we were interested in purity, but we can refine this to a different notion of safety. So we formalize this idea using the notion of capabilities. So capabilities are a well-known thing in the systems programming community. A capability is defined to be a token of authority. For example, a security token or a permission. In our impure language, a channel variable, for example, standard out, is a capability. Then we define the notion of capability safety. We say that a program is capability safe when it only performs effects using the capabilities it has access to at runtime. So for example, this function G is capability safe, but F is not. But G is not pure, it's only safe. So we'll come back to how we could encode purity using safety. But for now, let's try to extend our language with safety. So first, we want to distinguish between two kinds of variables, safe variables and impure variables. Safe variables are capability safe, and impure variables are just arbitrary variables in our language. So we use these qualifiers S or I in blue and red to annotate the bindings of variables in our context. Then we would like to internalize the notion of safety using a safe type constructor. We add a box type constructor, and we add two new term formers, box and letbox. So these are expressions, and we distinguish between expressions and values. Boxing an expression turns it into a value. We also have a new safety judgment, which we use to judge whether a term E of type A is safe in context gamma. So now we want to ensure that safe variables can only depend on other safe variables. So we add a substructural operation on our contexts. So this purify operation drops all the impure variables in our context. Then, if we know that a term is well typed in a safe context, we know that it's safe. And if we know that a term is safe, we can put it inside the box using our box introduction rule. And finally, we also have a letbox elimination rule for our box type constructor. So if E1 is a boxed term, we can bind the underlying value X, and we can eliminate to E2 if it is well typed in the extended context, where X is marked with a safe annotation. So these were the additional typing rules for the box type. Let's also take a quick look at the other typing rules. The rule for variables remains essentially unchanged. For functions, to introduce a lambda, we allow the bound variable to be impure, so that we can substitute arbitrary expressions. The lambda application rule remains the same. And then finally, the rule for print is just as expected. It's simply a unit. Now, at this point, we note that this box constructor is a comonad. It has a co-unit and it has a co-multiplication. And in fact, our syntax for adding comonads to our type theory is inspired by the classic Fenning-Davis paper on the judgmental reconstruction of S4 modal logic. Instead of dual contexts, we use annotations on our variables. And for more details on the syntax, see our paper. So coming back to our original motivation, can we use this notion of safety to recover purity? Well, we say that a function is pure if it is safe and it has access to zero capabilities in its environment. So, box of A arrow B is the type of safe functions, but they're not necessarily pure. And box of A arrow B is the type of pure functions. So going back to our original example, we can now write a pure variant of our map2 and map1 and map2 functions. We force the function argument to be pure, and it should be only applied to a list of safe expressions. We can use box and let box to rewrite the body of map1 and map2. So using this new definition for map1 and map2, we can show that they are provably equal in the extended calculus. Finally, to conclude, let me point out some of the main takeaways from this talk. First, we can use this notion of capabilities to encode effects and to control the usage of effects. This idea of capability safety, or denying the usage of a capability from the environment, can be captured using a comonadic type discipline. Let me also highlight some of the technical results in our paper. We formalize an effectful calculus and we extend it with a safety modality, and we show how to do substitution and so on. We show how to recover purity from capability safety, and we also discuss how to do capability taming, that is, how to incrementally add safety to an already impure language or a library. We give a categorical semantics for this language. It is given by a Cartesian closed category with a monad and a comonad, which interact with each other. We give a construction of capability spaces, which give us a denotational semantics, which satisfies the axiomatic categorical structure that we need for our semantics. The idea of this construction, in fact, comes from an old paper of Martin Hoffman. Also, capability spaces have more structure than we actually use for our semantics. It can be used to give a model of linear type theory, which we discuss in the paper. We also give the full equational theory for this calculus, and we use our denotational semantics to prove its soundness. Finally, we also show how to embed the pure simply typed lambda calculus into our language using this comonadic modality. This embedding preserves the equational theory of the pure SDLC. Also, we show that our language is a conservative extension of the SDLC. This is a requirement for a purely functional language that Amr Sabri told us about a long time ago. And yeah, that's all I had to say. Please see the extended version of our paper if you're interested. And thank you very much for listening.
Thanks, Vikraman. He is now available in both the New York and Asia time bands for question and answer.